Welcome once again to the Simpkins Physics Corner. It's the remix of the friction, hot and fresh out the kitchen. Here we go, a little friction for my academic physics folks. Let's get to the warm-up here. So in this video, I want you guys to pause and to go find this guy. This is Paul Hewitt, and we'll just take it right to you here, all right? So let's go check out Mr. Hewitt himself here, for educational purposes, of course. And as we check out this guy, this is college. We're going to play a little game called Are You Smarter Than a College Student? So this guy is teaching some college students. And he is going to take a block, and he is going to pull that block across a table like so. So he's pulling it at a steady or a constant rate. Now, let's see if you can guess how much friction there is. Here he goes. So as he pulls it across there, you can see it read about 3 newtons on the scale. And so he's going to ask this question. He says, well, if I pull on this block and it moves at a constant speed, if I pull on it with 3 newtons, and it's moving at a constant speed means the forces are balanced, which means if my pulling force is 3 newtons, then that means the friction force must also be 3 newtons backwards, because it has to be in equilibrium in order to go at a constant speed. All right, so let's hop back over to our slides here then, and we'll take a look at friction. This idea of friction is a force that opposes motion. We've defined it as that before, but let's get into the details of how this fleshes out. So here's the overview picture. If a strong man exerts 500 newtons of force on a box, and it moves at a constant speed, these words right here, constant speed, they are going to mean a lot to us. They mean that the net force, or the sum of all the forces, is 0. Not that there are 0 forces acting on it, but that if we add up all the forces, they add up to 0. So if the applied force, Fa, is 500 newtons, and I'm moving at a constant speed, what does that mean about the forces? They're balanced. And if the forces are balanced, that means that Ff must be equal to 500 newtons in the opposite direction. Because, remember, force is a vector, which means it has magnitude and direction. Oh, yeah! And if that's the case, Fa is equal to 500 newtons, but Ff, we would say, is equal to negative 500 newtons if we defined a positive as to the right and negative as to the left. And when you add 500 plus negative 500 together, what do you get? 0 newtons. Equilibrium, balanced forces, constant speed. Now I see. On the right, draw a free body diagram of the box only. So in this one, actually, I think it's on your packet. It does say the box it calls it a 1,000 Newton box. So just a reminder that newtons is a measurement of force. And so this is not the mass of the box. This is the, force of gravity of the box. Or Fg would be equal to 1,000 newtons. And that means Fn would be equal to that. And then, of course, we could put our two 500 guys on here. We have 500 newtons equals Fa. And we have negative 500 newtons equals Ff. So that would be like the full free body diagram. And then we already mentioned this. Is the box in equilibrium? Yes. Why? Because the forces acting on the box are balanced. We have 500 to the right, 500 to the left. They cancel out. So what actually is friction, right? Like what is, it's a force that opposes motion, sure. But have you ever thought about what it is? Like I know it's the thing that makes my hands get warmer when I do this. And I know that it makes things harder to push around on the floor if it's carpeted versus, maybe a hardwood floor. But what actually is it? So since you're at home, we won't be able to do this, but I want you to imagine doing this, all right? Let's take a partner or a student, and we're going to tie a rope. They're going to hold on to like a little ski rope here. And your job is to pull, you got to pull backwards like this, and you're going to try to pull your partner across the classroom. Now, let's think about some things we could change to make that harder or easier. Well, I have some students that show up in pajamas and moccasins every day to school. And if you have nice smooth mocks, right, that would be one thing. Then I got other students, they show up with like steel-toed boots with a nice grippy oil slip-resistant bottom to it. Well, that, of course, would make a difference. Would be the kind of shoe you're making, right? Let's say I take you and I put you on top of a wooden board. So you're standing and you're stuck nicely. Well, you have no torso, I guess, but you're having fun anyway. So you're standing here on the board, and I pull it. Your feet might stick to the board, but what do you think will happen between the board and our tile floor in our classroom? So you can start to think, and then think about this also. What if this person has a very large mass and this person has a very small mass, and they pull back and forth on each other? Which one do you think is more likely to slip or to slide or to move? And so when we think about all the different things we can manipulate or change, friction really depends on 3 things. Depends on the mass of the object, how big something is, right? If it's heavier, it might push harder on the ground, which means there'd be more friction. If it has the materials that are in contact and that's talking about the kind of surface. So do you have Uggs or Timberlands or moccasins, right, on the floor with your shoes there, or you're wearing your socks maybe. And then the motion of the object. And this one we'll talk about a little bit, but this is the idea that if you're already moving, it's easier to keep moving than if you have to get something moving from rest. And we'll talk about that here in just a second. So as you look at the friction equation, this is what it is, all right, and we're going to have to define some things. So FF is the force of friction. Fn, we already know, is the normal force. This thing, what is that? Well, for any of my Pokemasters out there, you know what this is. If you know, who's that Pokemon? It's a Mew. All right, it's a Mew. It looks like a little cat magical thing with a tail, right? And this is the Greek letter mu, all right? It's the lowercase Greek letter mu. It's basically like a little cursive U. Now, sometimes it ends up looking like an M, so you gotta be careful, but that's how I draw my Mews. And the mu is called the coefficient of friction. Now, coefficient means number, and friction, of course, is the thing we're talking about. And so all it means is friction number. Well, what do you mean friction number, Mr. Simpkins? Well, two surfaces always have like a set or a determined friction number depending on how rough they are, right? So if I take a block of wood, and then I take another block, but it has sandpaper on the bottom, all right? There's going to be a certain mu, or coefficient of friction, associated with that. If I take a rubber shoe and I put it on a tile floor, there's going to be a coefficient or a number for friction that determines how much friction there is between a rubber surface and a tile surface, and so on for any two surfaces you can come up with. They all have their own unique mu. Now, just a pro tip, these mu numbers usually are less than 1. There are some rare exceptions, but they are usually less than 1, which means they are decimal. So if you get a number that's like 27 for mu, you probably did something wrong. So let's see how this fleshes out with the equation. Go ahead and take a moment in your notes to write these down. FF means the force of friction. Mu means the coefficient of friction. This is the new thing for today. The new mu. Whoopie-doo. The coefficient of friction is the mu there. And then the normal force, Fn, is that perpendicular force pressing back up from the floor there. So those are our three pieces to the friction equation. Now, some people say, Mr. Simpkins, your class is beat. Physics is beat. And I say, no, no, no. I can mathematically prove to you that physics is, do you see it? Physics is officially fun. Physics is fun. You get it? Oh, man, I had so much fun. So there it is. There's your fun for the day. Let's have some more fun. Looking at an example. So it says we got sigma F equals ma is what we were talking about last time we were together, and then we have this friction thing. So let's put all this together. If you use a horizontal force of 30 newtons, so here we go, 30 newtons, okay, to slide a 12 kilogram. Now, careful. Kilograms does not measure force. Newtons measures force. But kilograms does measure mass. And we can find the, force of gravity from the mass. We can do 12 kilograms times 9.8 meters per second square. And that's going to get us our FG, or our weight of that object. So here it comes. It's 117.6 newtons. And if we're on the floor, a horizontal surface, that we can imply then that the normal force is also equal to 117.6 newtons. Rock and roll, dude. Now, but it does say, at a constant velocity. All right, so what does that mean? I'm going to pause for a second. What does constant velocity mean? That means the forces are balanced. And if that's the case, then that means friction must be equal to 30. Remember the little short video we did in our warm-up? If the applied force is 30, and the friction, and the friction force is 30, and you're moving at a constant speed, they must be equal to each other. All right, and so let's take stock of what we need. For the friction equation, we need to know FF. We just figured that out. We need to know Fn. Fn on any flat surface is going to be equal to Fg. So first we found Fg, then we got Fn. Cool. Now all we got to do is find the mu. And to find the mu, you just use the equation. So Ff equals mu Fn. And it's looking like 30 newtons equals mu times 117.6 newtons. Now, sometimes I get sloppy and I don't write the units, but I wanted to do it particularly here to show you something very magical. All right. If you notice that there are a newton divided by a newton, do you guys know what happens to those? They get annihilated, right? So do these. They get annihilated. And what does that mean, guys? That means that mu, that's why they call it the coefficient of friction, because it doesn't have a unit. You could call it a munit if you want, but no, it doesn't. It does not have a unit. It's just a coefficient. It's just a number that you multiply by. So it's not like it's in Simpkins's or quarks or newtons or anything. It doesn't have a unit. So mu doesn't have a unit. And what else did I tell you? I told you that mu is usually a decimal, which in this case fits that bill. It usually does. So there's a little sample for you guys. Now, let's talk about two different kinds of friction. I want you to leave today knowing that there are two kinds. There's kinetic and there's static. Now, you probably have heard kinetic before, maybe from middle school science when we talked about kinetic energy, right? Things that are moving. And kinetic friction, an example of that would be like if I took something and I pushed it and it was sliding across the floor. Of course, the friction would act to oppose the motion, but as the two surfaces are moving relative towards one another, that's the best way to say it, that's the static friction. Another example is if you're riding your bike. I used to do this all the time when I was a kid. You ride your bike and you just slam on the back brake, right? What happens? Your tire goes and skids across the road. That's kinetic friction because the tire is moving relative to the surface of the road. It's skidding across the road. Now, static, on the other hand, is static still, stuck, strong, or still. It's when you are stuck to the ground, you're still, you're not moving, you're static, and it's a stronger type of friction, and it's called static friction. And so if you are, let's say I have a giant thing on like a carpet. I have a giant refrigerator on the carpet. That's gonna be hard to move, right? So here's me with my wimpy little noodly arms here, trying to push it, and it just doesn't go anywhere, okay? That's static friction. The kind of friction that's opposing me, that's coming back this way, is called static friction. And so that, we all know, like if I ask you, hey, if you have a refrigerator sitting on the carpet, is it easier to get it moving or to keep it moving? If you've ever moved furniture in your life, which maybe if you rearranged your bedroom, moved a dresser or something, once you get it moving, it's easier to keep it moving. And so that's why static friction is stronger. It's when things are stuck or still. You have static, sticky, stronger, stuck, still. Static friction is stronger than kinetic friction. All right? So if we just consider this numerically real quick, if it takes 500 newtons of force to begin moving a large fridge, all right, what kind of friction is acting when you try to start moving the refrigerator? When you start it, static, stuck, sticky, stronger, still, that's your static friction. And based on what we just said, look at what we just said. We just said that kinetic friction is weaker, static friction is stronger. So based on what we just said, how much force will it take to keep the object moving? Well, now we don't have to worry about static. It's now kinetic, and kinetic is usually less. So that is how we can justify our answer there. We can say kinetic friction is generally weaker than static friction. So we don't need 500 newtons to keep it moving. We need less than 500 newtons to keep it moving. All right, so it takes more force to start something moving than it does to continue it moving. I will end with this one. I did include a video of anti-lock brakes, which given the season that we're in right now is a very timely thing to know about, but unfortunately for time's sake, I'll have to tell you about that next time I see you. So let's go to this one real quick. A child drags her toy across the floor. The coefficients of static, I'm going to use one color for static, and kinetic friction are these. It says how much force will she need to apply to start the box moving? Static, start. So those numbers are going to go with that. And how much force will then needed to keep it moving at a constant velocity? That's going to be that. I'm probably only going to have time for one of these, so let's do the first one. Well, in order to get it moving, the applied force has to be at least bigger, or at least as big as the force of friction. And we know that the force of friction is going to be determined by mu Fn. So let's go ahead and plug this stuff in. Mu is 0.32. Remember, we're doing this for the static or getting it moving piece. And Fn, life hack here, guys, remember, Fn on a flat surface is always going to be equal to Fg, which happens to be mg. So if I do mg, I'm doing 10 times 9.8, which is 98 newtons of force of gravity. That means it's 98 newtons for normal force. So I do 98 newtons right here. And if I go super speedy, I can type that into my calculator, and I'll get, it takes, the force of friction is going to be 3.136 newtons. So that's how much I'm going to have to push. Doesn't sound right. Oh, that's because I did 9.8. Silly Simpkins. Always check your math, guys. Don't do physics blind. Try again. 31.36 newtons. Much better. All right, so that's the static friction where it's going to max out, and so our applied force has to be equal to that to get it moving. To keep it moving, you guys see the math is going to be the same. It's still going to be mu Fn. The only thing that changes is the mu is now smaller, right? So you multiply those together like that, and the force of the force of kinetic friction is going to be a smaller number. It's going to be 24.5. So in this case, let's summarize it. You have to push this hard to get it moving, but then you can let up a little bit, and you only need 24.5 newtons to keep it moving. Well, I hope as you guys are outside in the snow, you're not slipping or sliding too much because that would be kinetic friction. But I hope that you are steady, stuck, and still working on your physics with some static friction. Mr. Simpkins in the Simpkins Physics